semantics for composable continuation from abortive to delimited control, and Pauli will give a talk.
All right. Hello? No. No? Hello?
Yep.
Okay, good. All right, so I'm going to kick off this session on context dependence by talking about effects that allow programs to manipulate their own flow of control, but in a way that still lets us work compositionally. So programs can refer to their context, but we don't want them to be so entangled that you can't separate them. So we still want to have all of those nice local equational reasoning principles that we can do for open programs like we have for the lambda calculus. And so to achieve this goal, we'll find that logic can be a really good inspiration, where the lessons that it teaches us allow us to fix problems that occur in programming languages. But moreover, this actually even works if we go about things in an untyped or kind of type agnostic mindset, that logic still applies. And so to begin looking at control effects, we could go all the way back to the classic operator from Scheme, calcc. And as it turns out, this operator corresponds to principles of classical logic in the same way that the lambda calculus corresponds to intuitionistic logic. And in order to understand what calcc does in a program, we have a similar situation that we have in logic. So there's two complementary approaches. We can either start with a pure language and then add primitive operations that give us the effects that we want, or we could start with a language that already has continuations and continuation variables integrated into its substrate from the beginning. And then we're going to get a little bit more advanced and go to delimited control. And so the change here is that we're able to bound or limit the scope that a control effect actually has over the program. And we'll also find that the continuations that it gives us, I mean, this is the other way to refer to it, they compose meaningfully like functions. They return results and we can do things with them. And these two little changes give us a tool that's vastly more expressive than just a classical control operator like calcc. For instance, there's Felinski's famous observation that if you have an effect that you can describe as a monad, you can use delimited control to simulate that directly in a program. So it's a very powerful expression mechanism for effects. And so we'll begin with the classical world of control effects and look at two examples of these complementary approaches. So there's a lambda calculus, where we add on top the calcc operator as a primitive. So that's one way. And then the other way is we start with lambda mu. So this is a language that has continuation variables integrated inside of it. And then, as it turns out, those two are the same thing. They allow us to write the same sorts of programs. And then we'll focus in more on the lambda mu and do a little syntactic relaxation that a number of people have done previously. Yeah, so it's you just write more programs with the stuff that we already have. But it turns out that little relaxation trick that we do with the syntax lands us in the world of delimited control, so a much more expressive setting. And it corresponds to a lambda calculus with delimited control operators. And in particular, this story of the two classical languages and the syntactic relaxation into delimited control works for a variety of evaluation strategies. This isn't just limited to strict functional programming languages like the usual setting for control effects, but it works for call by name, so lazy evaluation, and also with memoization and sharing as well. They all follow the same story in a single generic approach. So to begin, let's look a little bit closer at classical control. So to start looking at an operator like callCC, we can begin. So for now, we're just going to focus on the call by value lambda calculus and call by value evaluation for simplicity. And so we begin with the call by value lambda calculus, and we add on top a built-in primitive called callCC to represent that function. And we also add a representation of a reified evaluation context. And so one way to explain this is through an operational semantics, what a program does if you evaluate it. And so to evaluate a callCC, what that does is it takes a snapshot of our current evaluation context and then passes that along. And so this is the context in which it's called. And then when we then later refer to and call one of these reified evaluation contexts, it replaces our current calling context. So we swap out and go do something else. Another way that we could understand something like callCC or a control effect is through an equational theory. So this gives us a much more flexible way to reason about programs that may be open, they may contain free variables in them, so it's a more compositional reasoning technique. And so to do this, we could start with a theory, an equational theory for a call by value lambda calculus, and then add on top extra axioms that explain what that callCC primitive operation does. But if we do this, there's a bit of an issue. We'll find that the equational theory that we get doesn't actually align with the operational semantics that we started with that explained what it did. In particular, there are some programs that when we run it, we get to a value, but the equational theory is not able to reach a value. So, in particular, the equational theory is weaker. And the root cause is that how do we know that we actually have the whole context? So when we're thinking operationally, we cheat a little bit and we just say, I'm just evaluating the whole program, there's nothing else, this is it. But when we're working compositionally with something like an equational theory, we don't get that privilege. We might actually be sitting in a much larger context, and so how do we know? How could we do this sort of thing? So to address this issue, let's look a little bit more at the behavior of these continuations. So we said when we call the reified evaluation context, it replaces our current context. So we actually jump somewhere else in the program, effectively. And so let's codify that in the theory. So we can do that by adding some variables that are special and only stand in for a continuation, and they inherit this particular behavior. If we apply one of these continuation variables to something, then that causes us to jump somewhere else. And the thing to notice is that if we have a jump, it's going to be the same even if we're in a larger evaluation context. Inevitably, we're going to discard that and throw it away. It's garbage. And so in this way, the jump serves as a natural sort of bounds on the actual evaluation context that we ever would need to care about. It's a limiter on the extent of the actual continuation we'll use. And so let's try that example again. We had a term that we could that we ran to get a value, and so we could import that into a jump. We're just saying instead of that term, it's a continuation variable alpha applied to that term, and it still runs and gets us an answer like before, so that hasn't changed. But now we can use the compositional reasoning of the equational theory to also get the same answer out. So the fact that it's in a jump is enough to tell us we've got the whole context, the callCC is done. And so if we take this idea of a jump seriously, and the information it provides us about reasoning about programs with control effects, we wind up with a slightly different language called lambda mu. And we can see this as a bit of a change of notation and a bit of a syntactic restriction on our programs. So in particular, we distinguish the jump, so applying a continuation to something, as a separate syntactic category called a command. And then instead of callCC, we have a control abstraction that's notated by mu based on the original presentation of this calculus. And one of the big differences, aside from this change of syntax and restriction, is that we don't really run terms anymore. That's not the whole view of a program. We have a story now. What you run is a command. That represents the entire program and the whole scope of what we're going to be dealing with. And so historically, well, the lambda mu calculus was developed in the field of logic as a way to reason about proofs in classical logic as programs, similar to the way we can reason about proofs in intuitionistic logic as programs in the lambda calculus. And originally this was done in a sort of lazy way in a call-by-name evaluation strategy, but you can give it a call-by-value interpretation just as well. It's pretty much the natural thing. And the main advantage that this gives us is that the equational theory now actually contains our operational interpretation that we wanted for programs, so that there's not that same mismatch we had before. The operational rule on what a control effect is exactly one of the equations. So this gives us back our compositional reasoning technique that's operationally complete. But also, it doesn't cut out any of the interesting programs we could write. These two are equivalent. They're exactly the same theories for control. And so now we'll move on. Now that we've identified this interesting subset of the language, we're going to look at relaxing the syntax a little bit, relaxing our programs, and letting us write more with the tools that we have in the lambda mu calculus. So in particular, this is a traditional relaxed syntax. It's been done several times, where we collapse the distinction between a term and command. We just now start mixing them freely together. And we're going to interpret them with the same rules we had before. We're not adding any extra equations or axioms on what programs do. Instead, the only difference is, because we mix together two syntactic categories, we might find one when we expected the other. So we might find a command when previously we only had a term, or vice versa. So those are the only new equations we have in the system. So let's take stock. We haven't added any new constructs to our language. There's no new things we can use to write programs. It's still the same stuff. And we haven't added any new operational type rules that tell us what programs do. It's still the same behavior of that same stuff. And traditionally, these were considered type calculi, and they were equivalent in terms of their behavior. So, of course, they must be the same thing. No. As it turns out, if you ignore the type system and just take programs as what they are and run them, you actually get a language for describing delimited control. So how can we think about this? Well, so one of the basic ways to describe delimited control is through some operators, and a typical choice would be using something like shift and reset. And so what's the difference between shift and reset and the scheme control operator called CC? Well, the shift operation is bounded by the nearest reset in our program, so it adds a scope to how far it actually goes. And the continuation that it hands us will return. It'll actually return a value so that we can take it and do something else interesting with it. And so in particular, they compose like functions normally do. And so we can take a continuation and call it several times, get the result 7 times. So it's a more flexible abstraction over our contexts. So if we look at it this way, we've got an embedding of the shift and reset operators into the relaxed big lambda mu calculus, and one that faithfully respects the semantics. So we've actually captured the theory of shift and reset in this calculus. So the equational theories are the traditional one, and as well as the definitional continuation passing style transform, which was used to define the semantics of these operators. So it's really a language that allows us to express these things. And it kind of comes out naturally inside the framework. But there are so this embedding doesn't actually cover everything in the relaxed big lambda mu calculus. There are some terms which lie outside of that. So it's really a subset. So next we might ask ourselves, what would actually cover the whole thing? So we can look at a minor variant of the shift and reset operators, which are now called shift 0 and reset 0. These are much less studied, but more recently some interest has risen a bit more on them. And so the only major difference between it is that the shift 0 operator, when we call it, the surrounding delimiter, which provided a scope for the effect, gets removed. And so we can use several of these operations to dig ourselves out of many of the control delimiters. And so, if we look at these, we find that these two operations are equivalent to the relaxed big lambda mu calculus. Their equational theories are the same, their transformations are the same, and these operations critically rely on that mixing property of the two things. And so the conclusion is that this sort of taking an idealized, very simple sort of scheme-like language with just functions in call-cc, restricting the syntax to get a better defined behavior, and then relaxing it in the natural way, has actually led us from classical to delimited control. So from a much more restrictive way to describe control flow effects in a program to a much more expressive one. And so by looking at it in the bottom of this chart, it gives a sort of canonical path from classical delimited controls, sort of revealing that delimiter hiding inside of what's normally considered an undelimited continuation all along, that we do by ignoring the typical typed interpretations of these languages. And it also gives us an embedding of other operators like shift and reset too. But moreover, so we can look at both languages with many different control operators, but the important thing is that we still get all the nice observational guarantees that we have about them. For instance, the reset barrier for an operator like shift provides a very hard barrier. We'll never be able to cross it. It's a very strict, like a exception handling mechanism that you can't get across. So if we have more than one, it's redundant. Reset is idempotent. And so this is a guarantee you can provide, you can prove inside the language using the equational theory, but it still holds even if you use other operators that don't follow this same criteria. So it actually allows you to put together programs using different sorts of operators with different properties without having nasty surprises that would violate the strong guarantees we would want about programs. So it's a way to have abstractions with nice properties that programmers can rely on, and having it not fall apart under composition. And so there's several other things that's in the paper that there wasn't time to get into. In particular, I mentioned that the same story holds for other evaluation strategies, not just strict evaluation like a scheme or ML-like language, but there's a single generic story for them all. You can sum up several different evaluation strategies by extracting their essence and give a single theory for across all of them. And so we can still get nice reasoning principles that work generically across different implementation strategies, even if you're using control effects and things that correspond to classical logic. Other things are there's improved reasoning principles for control operators that are sort of exposed by this approach that we didn't have before. So it reveals more ways to understand programs that have non-trivial effects in them. There's a technique for comparing different things that relies critically on compositionality, which really makes life a lot easier when looking at different languages. And so, to summarize, it's basically about control flow effects. We can have them, and we can have our cake and eat it too. So we can both have very powerful expressive capabilities that allow us to write effectful programs, but have the same nice reasoning principles that we came to grow and love. We don't have to give that up. And we can also be generic of evaluation strategies. It doesn't mean we have to program in a strict language. We can do lazy as well, and still have the same properties of the pure language being preserved. It's also another reminder that compositionality is a really powerful thing, and that we want to keep it at all costs. And that logic can be a really wonderful guide, although sometimes it can help to look past our type-born biases that we might have and see things that were just lying there staring us in the face the whole time, that types were preventing us from taking advantage of. So with that, thank you for listening.
Well, I think one thing that I don't quite understand. So you said that in your calculus, lambda plus shift plus reset looks like less expressive than lambda big mu, right? Mm-hmm. And lambda plus shift 0 plus reset 0 is equal to lambda big mu, right? And you're stressing untyped settings. But in untyped settings, it has been proven that shift reset are expressible, actually more of a macro expressible as shift 0 and reset 0. So using either of them doesn't give any advantage, because you can always write a program that uses shift and reset, and a program uses shift 0, reset 0, or the other way around.
Yeah.
So they're actually equally expressible. So it's not less than equal, actually equal in both cases.
So I should be a bit clearer about what that means by equal. It's not just the programs you can write that when you run them get you the result that you want, but it's really equality of our reasoning tools about them. That's the big difference. It's not just an operational type of equality, but in terms of observational properties as well. So that's the big difference.
Sorry, the theorem that was proven was macro expressivity, right? So it actually showed that the converge, it is even more intentional than observational equivalence. So it has been proven they converge to the same thing, right? So I'm not sure what's your meaning of equality?
So the difference is the embeddings that I think you're referring to don't satisfy all of the observational properties that we would expect for shift and reset. So in particular, in that embedding, reset wouldn't be idempotent, especially if you add in the shift operator in some other part of the program.
No, and also depends on what you mean by observation. So observation is something that the program terminates or doesn't, or if the program prints 1 or prints 2, right? And whether something refers to is it important or not, it's not observation they usually do on the program, right? Because it's intentional, and observations concern extensional behavior of the program, right?
Okay, so the point is, though, you can have, if you use the multiple two resets, you could use a shift to distinguish whether or not I had 1 or 2. That's the big difference. Or sorry, shift 0. So the encoding doesn't guarantee those types of properties for you. This is about tools for reasoning about programs, not just encodings that we can compile to assembly code. But that doesn't mean that the tools for reasoning about assembly code will give us everything that we had to start with.
Okay, well,
yeah. We can take this offline.
But okay, so my second point.
No. Come on.
I think they were ahead of it.
Oh,
Filip Szyszkowski from Aarhus University. So I would like to take it a little bit in a different direction, in the direction of types again. So as you've mentioned in the type setup, lambda mu and the capital lambda mu are considered equivalent. Now what you've shown is that the untyped capital lambda mu is equivalent to lambda with shift 0, reset 0. Now we also know there is a nice type system for lambda with shift 0 and reset 0. Does this mean that we didn't see something in the structure of capital lambda mu, like was the type system that was used to cause?
Yes, that's exactly the point. Is that it was using a classical type system like classical logic, and that throws out the interesting delimited control operations as type unsafe. But using something more like the type and effect systems for shift or shift 0, you would be able to, you'd still express the same programs, but the type system would accept that, and you'd be able to run it and see these extra effects.
Right, so basically what you're saying is that we could potentially come up with a better type system, like more fine-grained type system for capital lambda mu that would also admit extra programs that the type system for small lambda mu would not, right?
Yeah, pretty much. It's a limitation of typing rather than semantics.
Okay,
yeah.
Cool. Thank you.
Hello. I think my question might be related to Philip's, except maybe more basic.
Mm-hmm.
So lambda mu has a pretty well-known type system, and but to get your equational course to define the delimited control operators, you needed to relax the syntax. So is there a type system for that? Is there like a different version of classical logic?
Yeah, so this would be more than classical logic in particular. The ones I know of are more type and effect systems. So the one for shift 0, it's sort of, so they kind of depend on the evaluation strategy as well. So the one for shift 0 is strict. There's also a type system for the big lambda mu in a lazy call by name way that admits these sorts of delimited control programs by Soren, who started studying the untyped calculus, but also it's typable as well with a more flexible type system.
I'm not sure this differs from the preceding question. So first of all, delimited continuations always make my head hurt. And I can believe that big lambda mu might make my head hurt slightly less. So thank you for that. But the question is, intuitionistic logic.
Yes.
Classical logic.
Yes.
Delimited logic?
Exactly. What is delimited logic? No, exactly. Like we have this wonderful story where we have the language and then the logic, and they both have they're both interesting in their own rights in their own worlds, and the same for classical, right?
So if you've written out delimited logic?
I don't know what that is. Like, what is a logic? I mean, we have type systems, but what is a logic interesting in its own right that it corresponds exactly to delimited control? So that's a really interesting open question.
Right, so it's still an open question.
Yes.
Good. I look forward to your answer.
So the next topic